Hello and welcome to this lecture. In this lecture, we are going to talk about symmetric matrices and the real spectral theorem. So, this is one of the first results where you will see how orthonormality and inner products come and make the world of eigenvalues, eigenvectors much simpler than they are otherwise. Okay, so that's how we are going to start. We'll see symmetric matrices, then we'll see Hermitian matrices, then we'll see normal matrices, but all of them share the same sort of philosophy. Everything goes to having an orthonormal set of eigenvectors. So let's look at that. Okay. So we've been thinking of an operator T. We've been studying an operator T from Cn to Cn quite a bit. It's represented by some matrix. We'll keep an orthonormal basis always. Okay. So we've been seeing that T is diagonalizable if there is an eigenvector basis in which the matrix of T is diagonal, right? So for T to be diagonalizable, you need a basis of eigenvectors. When you have a basis of eigenvectors, with respect to that basis, the matrix of T becomes diagonal, right? So otherwise, it's represented by a general matrix. It may or may not be diagonal. We saw that diagonal is very nice to understand. This we studied so far without inner products. There were no inner products involved. We were just doing eigenvalues, eigenvectors and all that without inner products. Now that you have inner product, we've already seen that an orthonormal basis, given that you have an inner product, an orthonormal basis is much simpler in many ways. Okay, instead of a general basis, if you have an orthonormal basis, the coordinates are easy to find. There are so many other things that become very interesting. So at this juncture, to marry the two ideas, diagonalizability and orthonormality, here is a very interesting question you can ask, right? What happens to the matrices of T with respect to an orthonormal basis? Okay, so that might be a question you can ask. And we've already seen this very interesting result. This is called Shor's theorem, which says for any operator T, there is an orthonormal basis with respect to which the matrix of T is triangular. Okay, so we already saw that for any operator T, there is some basis for which the matrix is triangular. And if the T is diagonalizable, then you even get diagonal. We saw all that before. But we also saw that Shor's theorem, which is a very nice theorem using the Gram-Schmidt orthonormality and all that. We know that for any operator T, there is an orthonormal basis for which the matrix of T is upper triangular, right? It's triangular is okay, right? So that's a good result to have. But then maybe I want to be asked the next question. The next interesting question is orthonormal diagonalizability, right? Do we have for some operators T, okay, for any operator T, is it possible to have a diagonal matrix representation with respect to an orthonormal basis? Okay, notice the difference between diagonalizability and orthonormal diagonalizability. In diagonalizability, I am not interested in orthonormality at all. I just want some basis of eigenvectors so that my matrix will become diagonal. That may or may not be possible. Now, I want to ask an even more intriguing question. Supposing T is diagonalizable, but I am not happy with just diagonalizability. I want orthonormal diagonalizability. I want, with respect to an orthonormal basis, I want the matrix of T not just to be upper triangular or anything, I want it to be diagonal. Is this possible? If that happens, what kind of properties that such an operator have? Is it easier to describe? See, if the diagonalizability is a slightly more complex property to describe. We don't have simple ways of characterizing diagonalizable matrices, right? So you have to find the eigenvalue, eigenvectors, and you have to see if you have geometric multiplicity equals algebraic multiplicity. It's all complicated stuff. It's not very easy. Our hope is we can identify orthonormal diagonalizability much easier, in a much more easier fashion than just diagonalizability. If I give you a matrix, right, if I give you a big matrix, it's sort of difficult to find out whether it is diagonalizable or not. But can we find out orthonormal diagonalizability easily? Okay, so that's the central question answered by these spectral theorems. Okay, and you'll see that there are very easy answers once you want orthonormal diagonalizability. Okay, so that's what we're going to see in the next few slides. Okay. Okay, so let's start as usual. In our first step, we'll start with R2, right? So we've always been starting with R2. So we'll start that way with R2. We'll look at a operator T from R2 to R2. Maybe it's represented by A, which is ABCD with respect to canonical basis, or any other orthonormal basis also okay, but we'll pick a canonical basis. Okay. So I will assume that T is diagonalizable. Okay, so which means what? If T is diagonalizable, it's represented by the diagonal matrix lambda 1, lambda 2 with respect to some eigenvector basis, right? So V1 is an eigenvector, V2 is an eigenvector, V1, V2 are linearly independent. I don't know about anything about orthonormality, right? I only know V1, V2 are linearly independent. They are both eigenvectors. V1 is an eigenvector with eigenvalue lambda 1, V2 is an eigenvector with eigenvalue lambda 2. So, in the basis V1, V2, the operator T is represented by a diagonal matrix D lambda 1, lambda 2 on the diagonal. Okay. So, we will assume T is diagonalizable. Okay. And again, to begin with, to keep things simple, we will assume lambda 1, lambda 2 is real, V1, V2 are real, everything is real, T is from R2 to R2, no complex numbers involved here, right. Okay. So, now I am going to gently ask this question, what happens if V1, V2 are orthogonal? Okay. Now, not just linearly independent, but V1, V2 are orthogonal. What happens then? Okay. So, a moment's thought will tell you orthogonal and orthonormal are actually the same. Okay. So, if V1, V2 are orthogonal, I can divide by the norm of V1, V1 divided by norm V1 and V2 divided by norm V2, and I make it orthonormal, right. So, orthonormal, orthogonal are both sort of same in this situation. So, we might as well ask the question, what happens if V1, V2 actually end up being orthonormal? Okay. So, we will first ask that question and then we will think about other things associated with it. Okay. So, this is the question I am going to ask. Okay. So, I have a diagonalizable operator T, but then I realize I also expect that the eigenvectors are going to be orthonormal, V1, V2 are orthonormal. Then what happens? What can I say about T? Is there something simple that I can say about T or A, right? So, that is my question. Looking at A, I should be able to quickly do something about this orthonormality, right. So, that's my goal here. So, let us see what else can I say about T if I know that V1, V2 are orthonormal. Okay. So, that is the first thing. Okay. So, let us assume orthonormally diagonalizable. So, T from R2 to R2 is orthonormally diagonalizable. This eigenvector basis V1, V2 is actually orthonormal basis. Okay. So, then what happens? I know this is the starting point, right. So, this is the starting point. I have put the eigenvectors in the matrix here. This is my S matrix. So, A times S is S times D, right. So, this is my basic equation here. Notice this equation. I hope you can see this equation here. So, it is quite easy to parse. If you look at the first column alone, A times the first column is lambda 1 times the first column here, right. So, that is okay. A times the second column is actually lambda 2 times the second column here, right. So, lambda 2 times the second column here. So, it is easy to see. So, A times S is S times D, okay. But now interestingly, now if you look at the inverse of this matrix, V11, V21, V12, V22, the inverse is actually the transpose, okay, because of the orthonormality property. Okay. So, think about this very, very carefully. It is very easy to actually see. Because the columns are orthonormal, the inverse of this is actually the transpose. Okay. So, notice what has happened here. This transpose has happened, inverse is the transpose. So, you can see if you take this matrix and multiply by the transpose, you will get identity. Okay. Why? Because of the orthonormality, right. So, the first row multiplies the first column, you will get 1. First row multiplies the second column, you will get 0, right. So, that is because of the orthonormality property. Okay. I hope you see that. So, the basic property that comes through because of the orthonormality is this one. The inverse of this matrix is the transpose. Okay. This S matrix that we have for changing basis. Okay. So, when you multiply by the inverse, we see that A becomes the same matrix V11, V21, then lambda 1, lambda 2 comes, and then the transpose comes. So, notice that this is the inverse, right. So, this guy is the same as this inverse. So, it is a transpose. Okay. So, now I can multiply through. Okay. If I multiply through, I get this kind of an expression. You can simplify this, it is just a multiplication, multiplying 2 by 2 matrices. You do that, you get this. And you notice this very, very interesting property now. Okay. So, this matrix A, what was the property it had? It had orthonormal eigenvectors. Once it has orthonormal eigenvectors, because of this AS equals SD property and the S inverse becoming the transpose, I am able to write A in terms of the eigenvalues and eigenvectors in this explicit fashion. Okay. So, now without this orthonormality, this will not be possible. You will not get the inverse as transpose here. The inverse in general will be a much more complicated expression, and it will not be a very simple expression like this. Because it became transpose, you get a very, very simple expression. Now, if you stare at this very, very closely, you notice that these two are actually the same, right. So, these two entries are the same. This lambda 1 V11 V21 plus lambda 2 V12 V22 appears in the 1, 2 position and in the 2, 1 position. So, this A becomes the same as A transpose. Okay. So, this arbitrary A that we started with, if it has an orthonormal eigenvector basis, then A will be A transpose. So, this is a critical and very nice observation. Okay. So, this is what we have shown. If T is orthonormally diagonalizable in this real world, then its matrix is going to be symmetric. A is going to be equal to A transpose. Okay. So, now if you look at A, okay, this is a very easy property to check, A equals A transpose. Okay. But notice what we have proven. We have proven only one direction. We have proven if it is orthonormally diagonalizable, if your T has an orthonormal eigenvector basis, then the matrix A is symmetric. Okay. What about the converse? Is the converse true? If I have a symmetric matrix, then is it true that T is orthonormally diagonalizable? In the R2 case, okay, we are still in the R2 case. That's the question we are going to ask. If that were to be true, imagine how simple it is, right? You look at the matrix A, you can immediately find out whether or not it has real eigenvalues and it is orthonormally diagonalizable. All you have to check is for symmetry. A equals A transpose is an easy thing to check. Okay, so let's check that out. Let's see if that is true. Okay, so I'm going to look at the converse now. We are still in dimension 2, still in the real world. Okay, so let's say T from R2 to R2 is represented by a real symmetric matrix A. Notice symmetric matrix, all you have to do is this B and B have to be the same. A and D can be arbitrary, and we'll assume B is not 0. See, if B is 0, then already this becomes diagonal, right? It's already diagonal and its canonical basis itself is diagonal. So, we'll assume B not 0 and then see what happens. Okay, so I'm starting with the real symmetric matrix and then asking the question, what are its eigenvalues and eigenvectors going to be? Okay, in particular, does it have orthonormal eigenvectors? That's what I'm asking. That's the converse I'm trying to ask. The eigenvalues are easy to find. This is a standard formula here. You solve it, and lo and behold, you see this wonderful expression that inside the square root, you get the sum of two squares. Okay, so the sum of two squares is always non-negative, which means the two eigenvalues are real. Okay, the moment you have a symmetric matrix A, B, B, D, the eigenvalues cannot be complex, they become real. Okay, so that's the first converse to what we had. If you have real eigenvalues, then you had the orthonormal eigenvectors A equals A transpose, we already saw that. Now, if A equals A transpose in the 2 by 2 case, then the eigenvalues are real. Okay, we are able to show that. This is a very simple computation with just the quadratic equation solving. We find that what's inside the square root is always non-negative, so you get both eigenvalues to be real. Okay, eigenvalues are real, that's okay. What about the eigenvectors? The eigenvectors end up being orthogonal as well. Okay, so here are the two eigenvectors. I've put V1, V2 here. You can go ahead and solve it. You know how to find eigenvectors, right? So you put in the eigenvalues, you do the subtraction, find the null basis, null space vector, etc. Right? So that's what you have to do. This V1 and V2, I have not made them orthonormal, but you can easily make them orthonormal. You divide by the magnitude of each of these things, they'll become orthonormal. But anyway, V1, V2 are orthogonal. Okay, so now we are on to something that's really nice. So if you have a real symmetric matrix A, then its eigenvalues are real, its eigenvectors are orthogonal. So what we have shown now is, if an operator in R2 to R2, everything is real, if it's represented by a real symmetric matrix, then it has real eigenvalues and it is orthonormally diagonalizable. Okay, it has an orthonormal basis of eigenvectors, so it becomes orthonormally diagonalizable. So at least in the R2 case, orthonormal diagonalizability is trivial to check. You just look at the matrix A with respect to an orthonormal basis, of course canonical basis is good enough. If that matrix is symmetric, then the operator is orthonormally diagonalizable. This is if and only if, it goes both ways. Okay, a very simple way to check orthonormal diagonalizability. Diagonalizability itself is a pain to check. Maybe in the 2 by 2 is okay, but in general it's harder to check. But orthonormal diagonalizability is very trivial to check in the 2 by 2 case. Okay, does this extend? Does this property extend beyond 2? It turns out it's true, but we'll come to that later. But I want to show you just one example to illustrate how these things work out, just to see the numbers a little bit instead of seeing an abstract result. Sometimes an example is good. If you start with this very simple matrix 1, 2, 2, 1, which is symmetric, you can quickly compute the eigenvalues. You see 3 and minus 1 eigenvalues, and look at the eigenvectors 1 by root 2, 1 by root 2, 1 by root 2, minus 1 by root 2. Okay, so these two, if you take a dot product, you will get 0, right? These two are orthogonal. Okay, so you can see that these are orthonormal set of eigenvectors. And then when you write A, I can write A as S, this is my S which has columns as eigenvectors, times D times the inverse of S, but then inverse of S is the same as transpose, right. So, V1 transpose, V2 transpose comes in this way, okay. So, this is my A, okay. So, now notice what happens now. So, notice this is a multiplication. I have columns here, I have the diagonal matrix lambda 1, lambda 2 here, and I have rows here. Rows are V1 transpose, V2 transpose. It turns out this product is the same as this expression, lambda 1 V1 V1 transpose plus lambda 2 V2 V2 transpose, okay. So, I want to show this a little bit. Let me just take one moment to show you why this is true. See, notice if you have A11, A12, A21, A22, and if you multiply by B11, B12, this is in general true. I just want to quickly show you why that happens. So, what is the product? The product can be written as A11, A21, outer product with B11, B12, just the matrix product like this, plus A12, A22 times B21, B22. Okay. So, this is a very, very interesting property. So, if you multiply through, what is the usual way of multiplying if you do element wise multiplication? A11 B11 plus A12 B21, A11 B12 plus A12 B22, right? A21 B11 plus A22 B21, and then you have A21 B12 plus A22 B22. Right. So, this is your product of these two matrices. You actually multiply these two and check, and you will see these two are equal. Okay. So, this is another way to do matrix multiplication. It is just very simple. You just take the first column, first row, multiply those two together, you will get a rank 1 product, right. And then the second column, second row, multiply those two together, and then you add these two, you get the product. Okay. So, this is a very curious and simple relationship. You might want to look at it and prove it. In general also it is true. Even if you have a any two matrix multiplication, you can take the first column, first row, multiply them together, plus second column, second row, multiply them together, add them, you get the matrix product. Okay. So, this is a very good way of understanding matrix product. Okay. Now, that is what I have done here. Now, the only complication here is this diagonal matrix lambda 1, which simply scales each expression, right. So, instead of V1 transpose, you get multiplied by lambda 1, this V2 transpose gets multiplied by lambda 2. Okay. So, this is a very, very, very interesting form for the 2 by 2 symmetric matrix. Any symmetric matrix you have 1, 2, 2, 1, right, in 2 by 2, you can write it in this format. Okay. Lambda 1 times the eigenvector transpose plus lambda 2 second eigenvector transpose. Okay. So, this is a very powerful property. This is actually called the spectral decomposition or spectral theorem that describes this. Okay. You can go ahead and substitute and see how this works out, just to show you, and you can see that this matrix is like this matrix works out like this. You subtract these two, you will get this. I am just showing you an illustration of how this works. In general, for any symmetric matrix, this is true, right. So, this form also makes powers very, very easy to understand and compute. See, one of the main reasons why we study diagonalizability is powers of the matrix. Now, powers are very, very easy, right. So, when you do A squared, because of the orthonormality property, when you multiply these two, the cross terms will vanish, right. So, cross terms will have V1 transpose multiplying V2. What is V1 transpose into V2? That is 0 because of the orthonormality property. So, you do not have to worry about any of the cross terms, only the corresponding terms you have to multiply. The cross terms will go off to 0. So, this will simply become lambda 1 squared. What is the multiplication of this with this? That is also very easy, right. You have got a V1 transpose times V1, which is just 1 because of the orthonormality, right. V1 transpose times V1 is 1. So, you simply get V1 transpose again. So, you can pretty much multiply this. When you square this, you can simply square the lambda and keep the V1, V2 the same. Okay. So, you will just get lambda 1 squared, lambda 2 squared. Any power also is true. Okay. So, A power k is simply lambda 1 power k, this V1 transpose plus lambda 2 power k, V2 transpose. It is sort of like a basis expansion in some sense, a very, very simple description. Okay. So, this kind of a thing is very, very common when you have orthonormal diagonalizability. You will see over and over again, we will look at results of this nature. Okay. Okay, so here is a illustration of what is going on in case you want to see in terms of the R2 picture. Okay, so here is my matrix 1, 2, 2, 1, and I have a canonical basis E1 and E2, and if I work with the canonical basis, it's sort of difficult to understand what's going on because E1 goes to AE1, which looks here, E2 goes to AE2, that looks something like this red guy is going to this dotted guy. But of course, if you go to the eigenvectors, things are very, very easy, right? So for lambda 1 equals 3, you have the eigenvector 1 by root 2, 1 by root 2, and then when you do A times V1, it is simply 3 times V1, right? So it's a very easy thing to describe when you look at eigenvectors. And V2, the eigenvector with eigenvalue minus 1, you've got V2 here, and V1 and V2 are perpendicular, right? So that's a nice thing to see. And then V2 when multiplied by A goes to minus V2. Okay, so notice how this description is really, really simple, and V1 and V2 are orthogonal. Okay, so if you have an arbitrary U in R2 and you want to find, so first thing is you can, instead of expressing this U in the canonical basis, which is a little complicated, you can express it in the orthonormal basis V1, V2, and that's very easy to do. You just have to do U comma V1, V1 plus U comma V2, V2, right? So this is my orthonormal basis, so the coordinates are very, very easy to determine. Now what happens when I do AU, right? So AU is simply 3 times U comma V1, V1, because AV1 is just 3V1, right? And then minus U comma V2, V2, because AV2 is minus V2. So notice how the understanding improves greatly for what happens with A. So, right, when A times U is simply as simple as this. Okay. So, when you have an orthonormal basis decomposition, it becomes very, very easy to find what happens to U. In fact, even A power k U is very, very easy, right? So, it will just, instead of 3, it will become 3 power k, and minus 1, it will become minus 1 power k. Everything else remains very, very exactly the same. Okay. So, this was with respect to R2. But what happens in the general case? In the general case, we are going to state what's called the real spectral theorem. Proof sketch, I will mention it later on in another context. For now, let me state the theorem and you'll see how powerful it is. Okay, an operator T from Rn to Rn is orthonormally diagonalizable if and only if it is represented by a real symmetric matrix A equals A transpose. That's it. Okay, orthonormal diagonalizability from Rn to Rn, when you have operators Rn to Rn, is very, very easy to describe. Just find a matrix for that operator T with respect to some orthonormal basis, and if you have A equals A transpose, you're done, right? So that's the real spectral theorem. Not only true for 2 by 2 we proved it, but for n by n we will do a rough proof, sort of a sketch later on. Okay, so this is a very, very, very powerful result. So this is what it means to have a real symmetric matrix. When is the matrix asymmetric? On the diagonal you can have arbitrary values, but then upper and lower values have to be symmetric. Okay, A equals A transpose. So you notice here A12 comes here and here. Okay, both these values are A12. Okay, and then these two are exactly the same, right? So this row A12, A1n is the same as A12, A1n here, A2n comes here. So about the diagonal, it's symmetric on either side. Okay. So what do we know about a real symmetric matrix? It has real eigenvalues. So typically when you have real eigenvalues, people tend to order them. So they'll write lambda 1 greater than or equal to lambda 2, so on till lambda n. Okay. So they're all real, so they can be ordered. And then we have orthonormal eigenvectors. Okay, so it's got for lambda 1 you have an eigenvector v1, v2, so on till vn, and these are all real valued vectors because we are thinking of Rn to Rn. Lambda 1 is real, norm of vi is 1, and then vi vj inner product is 0 when I is not equal to j. Okay, so this is the sort of the description for real spectral theorem, and any other matrix in this world will not have orthonormal diagonalizability. If A is not equal to A transpose, you will simply not have orthonormal diagonalizability. Okay, so that's the real spectral theorem. Okay, so let's think of this decomposition. I remember I gave you a decomposition. You start with an n by n real symmetric matrix. You have these ordered eigenvalues and then the orthonormal eigenvectors. You can write A as S D S inverse, right? So S is my in the columns are the orthonormal basis of eigenvectors. Now S inverse becomes S transpose. Right. So this is the crucial property, S inverse becoming S transpose. That's because of the orthonormality of the columns. You can see you multiply these two, you will get identity. S and S inverse, you will get identity. It's very easy to check. You better multiply S inverse with S, and then you will get identity, and S inverse S is the same as S inverse. So it will end up being identity. Okay. So now using our matrix multiplication property, this becomes the same as lambda 1 times V1 V1 transpose plus lambda 2 times V2 V2 transpose, so on. So this is the general form of any symmetric matrix. Okay, so that's what the spectral theorem is telling you. any symmetric matrix has to have this form. There has to be some real lambda 1 to lambda n. There has to be an orthonormal basis in which you can write it as V1, V1 transpose, V2, V2 transpose, like that. Okay, you can add it up later. Now, this also tells you something about powers. Powers are very, very easy again because the cross terms vanish. A square will simply be lambda 1 squared V1, V1 transpose to lambda n squared V1, Vn, Vn transpose, and that way any A power k is also just lambda 1 power k Vn, Vn transpose. Okay. So, this gives you a very, very, very simple picture of understanding symmetric matrices, and that is why symmetric matrices, their powers, their structure is very, very, very easy to describe in general. Okay. So, here's an example, just a crazy example that you cooked up, and you can go through, find the eigenvalues and orthonormal set of eigenvectors, and you can write a general form. The general form A ends up being 4 V1, V1 transpose 2 V2, and you can write it down, you get like this. Okay. So, this general looking A can be written as the sum of these three matrices, and then any power is very, very trivial to write down as well. Okay. So, that is a simple example. Sometimes it is good to see an example to see what I really, really mean. Okay. So, here is a picture just to drive home the point. Okay. Once again, the picture that we have here for Rn is if you take any u, how does it get transformed through a symmetric matrix A? Okay. So, you may ask this question. So, if you have an arbitrary u in Rn and you have a symmetric matrix A, how do you describe the transformation by A? U first has to be written in terms of the eigenvector basis. Okay, and that is very easy because the eigenvector basis is orthonormal because A is symmetric. So, you can simply write inner product u v1, v1 plus so on, and now AU is very, very easy to describe. How do you do AU? For AU, you just take all these guys, scale them up with lambda, and then add them up, you are going to get AU. Okay, so that is it. So, the inner product remains the same, you just get multiplied by lambda 1 to lambda n. Okay. So, this makes it really, really simple to evaluate even A power n u, right. If you have A power k u, this is lambda 1 will become lambda 1 per k. Okay, everything else remains exactly the same. So, here are some problems. So, for instance, this given symmetric matrices, you have to compute A power 100x. Okay, so you do not have to multiply A with itself 99 times, right. So, you find the spectral decomposition. This kind of decomposition is called spectral decomposition. Find the spectral decomposition. If you know the lambdas, you simply raise it to the power 100, you will get the answer. The next question is sort of similar. What happens to A power kx as k tends to infinity? You find A power k and then tend it to infinity in general. Okay. So, some properties of symmetric matrices, if A and B are symmetric, which of the following are symmetric? You can see A plus B will be symmetric, A cube will be symmetric, A plus B power 5 will be symmetric. What about AB? Will AB be symmetric all the time if A and B are symmetric? Think about it, because AB transpose becomes B transpose times A transpose. A and B are symmetric, so AB whole transpose becomes BA and not AB. Okay. And BA may not be equal to AB, so it may not be symmetric. So, AB, it does not look like maintains symmetry if A and B are symmetric. Okay, you may want to look at it closely. Okay. So, here are other questions. If you remember, when you look at the matrices and their algebra, the powers behaved very differently from numbers, right. But for symmetric matrices, sometimes it is simpler. Okay. So, if you look at A power 5, so if A is a symmetric matrix, if A power 5 is 0, then A has to be 0. Okay. So, you can think about why that is true, because you have the lambda power 5, each of the lambda should go to 0. The lambda power 5 is 0 means lambda should also be 0. So, once lambda is 0, A becomes 0. So, if A power 5 is 0, A will be 0 if A is symmetric. And likewise here also you can see when lambda power 4 has to be equal to lambda squared, right. That is what has to happen, and that will give you some possible values for lambda 0 plus 1 or minus 1. I think is the answer there. Okay. So, these are some problems, and you can see how the spectral theorem is useful in answering many questions about symmetric matrices. Okay. Thank you very much.